Okay, yeah, welcome everyone to today's colloquium. So today it's our great pleasure to have Dr. Raman Sundrum from University of Maryland to give us a talk. Raman got his PhD from Yale University. He was at Johns Hopkins University as a professor for about a decade. Then he joined the University of Maryland as a distinguished university professor and the director of the Maryland Center for Fundamental Physics. So Raman has made many important contributions to particle physics and cosmology. In 2019, he was awarded the Sakurai Prize in Theoretical Particle Physics by the American Physical Society. Raman is also an elected fellow of the American Physical Society, a fellow of the American Association for Advancement of Science. So today we're very happy to have Raman tell us about cosmology and unification.
Great, thank you. So let me share my screen. I think it's still catching up somehow. There's a little bit of a delay. Let me, there we go.
Good now.
Good. Okay. So it's great to be here virtually. So I wanted to talk about some work that I did with my students, Shobhik Kumar, who is, however, now a postdoc at UC Berkeley, and Rushi Bodas, who is still a student of mine. And this is the first time I'm giving a colloquium on this, so you will be my guinea pigs. So the subject lies at the intersection of two extremely ambitious programs of research. One is sort of what I'll call extreme particle physics, and the other is what I'll call extreme cosmology. And even though they seem to live in different arenas, you'll see that they come together here. And I think the subject I'll talk about will certainly be one of those subjects that will lie, sort of at the most ambitious tail of each of those subjects. Very good. So I will be able in 1 hour to give you a kind of thumbnail sketch and some metaphors, but hopefully I'll convey the sort of mind-boggling nature of the subject and even the beauty of the subject. So this is a ancestral map of fundamental forces. But you should think of this picture the way you think of one of those ancient maps of the world, where when some ancient people were trying to draw the map of the world, they combined what they actually knew, what they had actually explored, with some of the clues they had and some of the guesses they had, and basically put together what they thought was the map of the world. And this is the map of fundamental physics in a kind of schematic way, the way that, as best we understand it, with the information we have, as well as our best guesses. And so this is the way a cosmologist would view it, where this is time, cosmological time, or if you want, dropping temperatures. And sort of what you see is that the one ring that rules them all is quantum geometry, or quantum dynamical space-time, okay? And this is the root of this family tree. And from it, everything bifurcates out. So there are the forces of nature and gravity, and then the forces of nature split up, and somewhere in there may be dark sectors that involve dark matter and so on. And each of these bifurcations in time, as the universe cools and expands, is some sort of a phase transition, a cosmological phase transition in the entire universe. And so this is the way a sort of a cosmologist would look at the sort of anticipated map of the universe. But if you look, a particle physicist sort of approaches this map upside down. They look at it like this, where in this direction, it's sort of energy scales or log scale energy. And our collider energies and non-collider experiments on Earth, terrestrial experiments, are basically coming from this bottom up, and for them, quantum geometry or string theory or whatever, that's like Mount Everest. And there we are still sort of at the foothills. And just to give a sense of scale, our particle colliders are sort of probing energies of order 10 to the 4th GeV, say the LHC, and the Planck energy, which is sort of the summit of this picture. The Planck energy made out of these constants of nature, the speed of light, Planck's constant of quantum mechanics, and Newton's constant of gravity, is pointing to an energy scale of sort of 10 to the 18 GeV. So we are drawing the map as we sort of anticipate it, but we may be wrong, which is why we want to experimentally explore this whole terrain if we could, if only we could. But here we are, humanity is way down here. And so what can we do? What more can we do? Now, as I said, each of these sort of, from the particle, maybe I should have said that, from the particle physics point of view, each of these phase transitions is something that we would call like a Higgs mechanism. But when you think of it cosmologically as a phase transition, these phase transitions, if they're violent enough, we may actually get information from them in the form of gravitational waves that are created by by the bubble dynamics of these phase transitions, in which case we may see them in future generations of gravitational wave detectors. So that would be another exciting way to probe this picture. But that's another colloquium. Maybe Yanu should give it because she works a lot on that subject. Actually, I'm talking about this other aspect that we can use very early cosmology, very early in the universe cosmology, or so-called inflationary cosmology, to probe energy scales which are just unthinkable from the point of view of conventional colliders, and are starting to get within striking distance of the summit here, but already able to presumably see exciting things that we would have no other way of seeing. Okay, so that's what this talk is about. Okay, so here's my quick outline. The first thing is I want to tell you about the magic that is behind this very boring sounding name, particle collider. But there's actually a piece of magic underlying it, a lot of magic underlying it. And if you want, the magical incantation is E equals MC squared. Okay, so I want to tell you about that. And then I want to tell you about sort of what I'll call the elements of modern cosmology in cartoon form. And then sort of this area of cosmological collider physics, the interface of particle physics and cosmology, which may, I hope, will be one of the great ambitions for the 21st century in both subjects. Then I'll talk a little bit about my work, maybe towards the last third of the talk, in terms of, there's a sort of a window of opportunity that you're going to understand when I explain this. And in that window of opportunity, you'd like to open the window a little bit more. And so I'll talk about some of my work in that regard. And I'll also talk about trying to apply this window of opportunity to exploring some of the most ambitious particle physics that we can imagine, for example, and that is motivated, like grand unification of the forces, gauge theories, such as the Standard Model is already made of, higher dimensional space-time. Can we experimentally explore these ideas using cosmology? That's what I will tell you about. And then finally, yes, again, there is a sort of window of opportunity, and some things that we're interested in are not in that window, apparently, but there's a way of sort of climbing into the window. And I wanted to tell you that mechanism if I have time. Okay, so a little bit of special relativity, okay? The fourth dimension, as you know, is time. Time is the fourth dimension. And so here is time vertically in seconds, and here is distance or space measured in light seconds, okay? Light second, of course, is the distance traveled by light in a second, which is to say it's 3 times 10 to the 8th meters. But if I use these units, then a light ray would look like this. It would trace out a line like this in space-time. At 45 degrees, basically it would travel 1 light second per second. Okay, obvious by definition. Now, as you know, all forms of matter, anything with mass, has to travel slower than the speed of light. And that would be indicated by something like this. Okay, it travels more in the time direction than it does in the space direction. That is to say, it's traveling slower than the speed of light. It's more vertical than 45 degrees. Great. So that's something that all of you know. I just wanted to put it in pictures. And here I'm drawing a picture of going forward and then going backwards, just drawing it in space-time. So here is some form of matter, maybe it's you, and you're walking in the forward direction. So as time goes on, you're moving in this direction. And then you change your mind, you forgot your lunch, and you go back home, say, okay? So that's changing, but now we call time the fourth dimension because it shares some of the properties of space. So we can ask, can we actually change course in the time direction? Can I say be going backward in time and then change course and go forward in time? So it's not something that you see in everyday life. And that's because there are some absolutely central obstacles to doing it, okay? In fact, there are two, and so here they are. So the first thing is that you'll notice, maybe I should have, let's go back one step. One of them is obvious here, which is in order to go backwards and then go forwards, maybe this is more vertical than it is horizontal. Maybe this is more vertical than it is horizontal, but somewhere in the middle, you will have to have gone faster than the speed of light, okay? You're gonna have to go faster than horizontal, than light does. So that's not an impossibility when you include quantum mechanics. Because in quantum mechanics, as long as you make this turn, as long as you make this U-turn in a small region of space-time, you can do it. Why? Because in sufficiently small regions of space-time, the quantum uncertainty principle kicks in, which says that you cannot know velocities and positions and times with infinite precision. In fact, it's not that you can't know them, they're not even well defined. Okay. And if you have kids or you are a kid, then you know that whenever the rules are not well defined, you will take advantage of them. Okay. And the same thing happens here. When there's the uncertainty principle, you will take advantage of it. So this obstacle to reversing course is not an obstacle as long as you do this business in a small region given by Planck's constant, the mass of the particle, and the speed of light. Okay, but there's another obstacle, and that is so before relativity there was energy and there was momentum, and they were apparently different things. But once we see that, we are in the relativistic world, energy is really just momentum in the time direction. Okay, it's like the fourth component of momentum. And the important point, the meaning of E equals mc squared, is that matter carries a kind of minimal momentum in the time direction, E equals mc squared. So if this particle was to go backward in time, it would be carrying momentum, which is at least minus mc squared, and then it has to change, and it has to carry momentum mc squared in time. As you know, if you are trying to change if you're trying to turn say a runaway truck around, even if it's only going at 5 miles an hour, it has enormous momentum. And it's very, very difficult to do. So it's very difficult to turn around something with a huge momentum. The c squared, the speed of light squared here, tells you that matter has enormous momentum in the time direction. So it's not an easy thing to turn it around. And the fact that you have to turn it around quickly makes it even harder, okay? But that doesn't mean it's impossible, okay? Because everything has a price. And clearly the price here is we need to sort of inject momentum, by which I really mean energy. We need to have momentum in the time direction to kick this particle from backward to forward. So we need to pump in energy, and the amount of energy should at least be this 2mc squared of this blue particle that you want to change course. And you need to concentrate that energy into a tiny region. Okay, so that's the game plan. But if you do it, you can create quantum mechanically by pulling things from the future and pushing them back forward in time. You can make anything you want. You can make things that are very precious to you. For me, I'm a particle physicist, so a top quark is precious. But you can make anything, and I'm making no qualifiers. You can make anything you want, however precious, however exotic, however rare it is in nature. You can make it like this, except you have to provide the appropriate amount of E equals mc squared. Okay, you want a car, you have to put in this, and c squared is huge. Okay, and it's a quantum mechanical event, so there's some probability for creating it. If you do this enough times, all your wishes can come true. There's no qualifier other than the energy bound. Okay, somebody is asking me a question.
Yeah,
Yes, this is I will answer that question in just a second, but yes, it is. But it's a useful way, and I think a faithful way of saying what's going on for people that are not technically in this game. So this is the answer to the question that was just asked. But basically, this weird thing, I'm talking about particles going backward in time. Nobody else talks about particles going backward in time normally, but that's because we give it a more conventional name. It's antimatter. Okay, antimatter is essentially the stuff you're making, matter going backward in time. So you can instead not sound crazy, and I know I must have sounded crazy. You can not sound crazy by instead saying, yes, if you pump enough energy into a small region, you can create matter of any type you want with some probability, as long as you create some appropriate amount of antimatter at the same time. But that's really cool. Okay, it's still a kind of magic by whatever name you want to give it. That's exactly what is done at particle colliders. For example, the famous CERN Large Hadron Collider does exactly that. For example, very, very common stuff, like the stuff you're made of, protons, are collided by racing around. In this picture, you'll see underground, under Switzerland and France, there is a race course for protons. They're accelerated in opposite directions and smashed, and then seen by these giant detectors. But basically, here are the protons smashing into each other with enormous energy. That's the injection of energy, and the protons have to be aimed so that at least parts of the proton, quarks and gluons, collide in very small regions of space-time, so that you can say produce something that's not sitting inside the proton, like a top quark. Okay? It costs a lot of mc squared to do, but the LHC is even more powerful in terms of the energies it can bring to bear. It's not perfectly efficient in this process, but it has more than enough to do the job. Okay, and in this way, for example, even more complicated processes in space-time, where you're creating a pair of top quark, anti-top quark, which are reannihilating and creating a Higgs boson. This is one way in which we have created the central player in what is known as Electroweak unification. Now, I'll talk about unification later, but this unification I put in quotes because it's not quite a full unification. It's kind of a major, I will call it intertwining of electromagnetism and weak interactions. But still, it's like a major discovery in physics. And here, for example, is the CMS particle detector and a Higgs candidate event seen there with a lot of splatter. That's the inefficiency. And then the decay products of the Higgs boson showing up in these green lines, they're photons. And so this is a way in which we explore some of the, some of this map that I was talking about. We explore some of the great themes in particle physics, like the Higgs mechanism. There are many other themes that particle physicists are trying to explore in collider physics. For example, we're trying to recreate dark matter particles. We're trying to create and study the particles that ultimately determine why is there more matter than antimatter, given that they seem to have, one seems to be, the other guy going backward in time, but why do we see more matter than antimatter? That's something that Janu and I have worked on in the past. Or superparticles, which are particles related to kind of fermionic dimensions, which sounds crazy, but is likely true in some regime. That's probably a true part of nature. So these are very exciting things that we can pursue in particle physics. But now let's talk a little bit about cosmology. And so again, time is still going forward, and space, well, I can only afford 2 dimensions to draw space. So I'm drawing it 3-dimensional space, looks like a 2-dimensional sheet. And here we are today at this moment in time with galaxy clusters all around us, and we're in one ourselves. And of course, it looks like all the galaxies are receding from us. Of course, we know better. What's really happening is that the entire space is stretching under the laws of general relativity. And so all galaxy clusters are getting away from all other galaxy clusters. There's no special place, and we're certainly not special in that regard. So presumably tomorrow, the galaxy clusters will be more diluted. But I'm more interested in the past here. So if we go back in the past, then the density of matter today, as the universe is expanding in the future, it's contracting in the past. So the density of matter today is relatively not dense. There's lots of empty space between matter. But as we go back in time far enough, the matter will get crushed together at super high densities, much higher than today. And we will just have a hot, dense cosmic soup of elementary particles. There, I've drawn it, okay? And if you go back even earlier than that, then at some finite time, you're going to hit infinite densities, or in other words, theoretical physics has lost track of what's happening. We don't know, okay? It's the unknown terrain for us, okay? That's the Big Bang. But this idea that there is a Big Bang singularity is actually avoidable, or at the very least, preponable. If you're going backward in time, I'm saying you can delay it. You can push it further back down here. Because this going to infinite density is partly because space-time is contracting as you go backward in time. And there's a lot of stuff which is going to infinite density, namely all the matter and radiation in the universe. If we could somehow do some magic and get rid of the matter and radiation before we hit the Big Bang, then we can actually avoid the Big Bang. And there are scientific reasons why that is useful, at least some of which will come out in this talk. So let's try it. Can we avoid it? And of course, we know how to avoid it, because if you're getting rid of matter and radiation if you're getting rid of matter as you go backward in time, when you're talking forward in time, that's like saying, oh, just create the matter at some time, right? Well, we already learned the secret of creating the matter, okay? So this is the picture. If somehow at some time, which is usually called the reheating time, matter was created in this way that I've shown you before, so that it didn't exist as matter and radiation prior to this point, then as you go back in time, you don't hit the Big Bang, okay? At least you can continue to do physics as we know it. Now, this seems to only, and this is sort of what I'm calling the inflationary paradigm, or the mostly, I would say, the generally accepted modern paradigm for cosmology. But there's a catch. How could you create these particles like this unless you provided the energy? Just like in collider physics, something must provide the E equals mc squared to create these particles at this particular time, okay? So who is it if it's not more matter and radiation, okay? And the answer is, it must be something that doesn't look like matter and radiation. It must sort of fake looking empty. And yet it must have an energy, a so-called vacuum energy. So it's some sort of quiescent state, something that looks like it's empty space, emptiness, and yet it's not really empty, but it does a pretty good fake of it. And it fakes gravity enough, it fakes the laws of general relativity enough not to create a Big Bang singularity, okay? So it seems to have backed up this question to this mystery. We have models of what this could be, but we don't have experimental determinations yet of what exactly is this mysterious vacuum energy that is creating all this stuff at the reheat time, okay? But we know some things about it. Sorry. Let me go back there. That even though it looks like empty space to some extent prior to this reheat time, secretly, there must be a kind of alarm clock in the universe, because whatever, something has to tell the universe, it's time to reheat the universe. Boom. Instead of sleeping in this quiescent state, it's time to suddenly, wake up. The universe has to wake up and you create all of the particles and matter and radiation in the universe. There must be a secret alarm clock in the fundamental physics there, okay? But it has some sort of energy, vacuum energy, okay? Well, what do we know about it? Well, one thing is that even back in Einstein's days, the idea of a vacuum energy coupled to general relativity was seen to have a rather classic kind of space-time geometry, which is usually called de Sitter space-time. And it's a slight modification of Pythagoras' theorem, where the distances are exponentially expanding. It's an exponentially expanding universe. That's all it is. So as time proceeds, the distances are getting stretched. And this exponential expansion is called a period of inflation. It's called the era of inflation, okay? And it's prior to the reheating time. This parameter h here is called the Hubble scale of inflation. You may have heard of the Hubble scale even in our current universe. That's not what I'm talking about. That's an almost negligible thing compared to this. Whenever I use h here, it's going to be the Hubble scale during the inflationary era. And it is a kind of gravitational energy induced by the vacuum energy, but smaller, okay? This seems to be a bit confusing. I've invoked mysterious thing number one, called the vacuum energy, right? Which is going to be dumped into creating particles and radiation at T reheat. But even prior to that, the expanding space-time itself has a kind of energy to it. And that's this Hubble scale. The fact that it reflects the vacuum energy and yet it is a distinct thing. I just want to make an analogy that's more familiar. If you talk about the energy of the Earth, then one way you can calculate it is you can calculate the mass of the Earth. Let's do a crude calculation. The mass of the Earth, which is the number of atoms multiplied by the mass of the atoms. And then if you say, well, I want energy, then you'd say, oh, it's mc squared. So it's the mass of the Earth in atoms times c squared. Great, that's the energy of the Earth. But there's a correction, which, by the way, we are experimentally sensitive to. There's a correction, which is the gravitational, the Earth is bound together by gravity, and there's a gravitational binding energy, which you can work out. If you just assume the Earth has, say, constant density, then just using Newtonian physics, you can work out what that is. And it goes like the mass of the Earth squared, and then there's G Newton and the size of the Earth and all of that. And if you put in the numbers for this, you'll find that it is many orders of magnitude smaller than this, okay? So it's a distinct thing. It's the gravitational binding energy relative to this, okay? In the same way, the vacuum energy is sort of analogous to this. The vacuum energy of whatever this weird state of the universe is has a kind of gravitational reflection or back reaction, and that's given by this energy scale H, okay? Now, the reason I point that out is because I want to now remember quantum mechanics. Wait, what about quantum mechanics? And this energy H, which is the energy of space-time itself expanding, it's a kind of energy, and it is good enough to sort of power quantum creation processes. So instead of having to have the LHC colliding particles to create the energy to create new stuff, you don't even need any particles in the initial state. Just the expansion of the universe is enough to create particles, okay? And because of this sort of law of exponential expansion and quantum mechanical creation using H, you can think of the process of creating during this era as, and it's trace amounts because it's the smaller energy, right? It's the lesser energy compared to vacuum energy. It's what you're doing is you end up creating particles and antiparticles, and then they expand and dilute away from each other and their wavelengths get stretched. And then you create, in the next time step, you again have quantum mechanical creation, and then that expands and dilutes. And you keep doing this. And if you keep doing that, if you keep scribbling on a piece of paper and then stretching it, and then scribbling on a piece of paper and stretching it, and scribbling on a piece of paper and stretching it, you'll get a fractal, okay? The fact that quantum mechanics is a probabilistic theory tells you you're going to get a random fractal. But the main thing is it's going to create a pattern that looks spatially self-similar on all length scales. It's something that, a property that we just call scale invariance, okay? So this is an exciting thing that we know even without knowing the details of the alarm clock mechanism. We have theories of that form, but we don't have experimental verification of any of them. But this we sort of would expect, okay, that we have scale invariance in this pattern of quantum corrections. So let's take a look at what that looks like. In our early universe, here's the reheat time. And now you can have energies of order, the Hubble scale of inflation, creating pairs of particles, okay, which then go up to this reheat time. And the particles that we want to focus on are the so-called inflaton particles. And what do I mean by that? I mean the particles that make up whatever the cosmic alarm clock is made out of. Okay, there must be some mechanism for making this mysterious alarm clock of the universe. And whatever particles it's made out of, I'm calling them inflatons. And we're imagining that you create pairs of them. They must be created quantum mechanically. The analogy here is like somebody says, I have a whole set of alarm clocks to wake up the entire universe. Okay, the entire University of California is being woken up. Every student has their own alarm clock, and they're all synchronized perfectly. But then quantum mechanics comes in, and there are quantum jiggles that are making the alarm clocks a little bit non-synchronous. And so in different parts of the universe wakes up at slightly different times, okay? That's why I've wrinkled this reheating era, okay, a little bit forward in time, a little backward in time, depending on where you are. And you can think of this reheating era as a kind of surface. It's a three-dimensional surface in four-dimensional space-time, and it's getting a little bit wrinkled by these quantum effects, okay? Okay, so it's not a perfectly uniform universe anymore. It's got wrinkles in it, okay? So you might say, look, I see particle creation, trace amounts of particle creation during inflation, and I see abundant gangbuster particle creation at the time of reheating. And I'm getting confused. What's going on? And remember, this trace amount is being created by just space-time expansion, by this sort of gravitational energy. And whatever this vacuum energy is, or the alarm clock of the universe, it's dumping, it's like a dam bursting, and it's creating tons and tons of particles out here. Now, this turns out to set up a very beautiful kind of cosmic laboratory, which is related to how we understand the cosmic microwave background, or CMB, and the large-scale galactic structure of the universe. Let me explain. So this is sort of, in the inflationary era, is a kind of quantum mechanical lab with just sort of trace amounts of quantum pair production going on. But because the particles I'm talking about are the things out of which the cosmic clock is made, they wrinkle this reheating surface, and the wrinkling of the reheating surface affects this enormous particle creation, okay? Which means that you have a kind of photomultiplier effect, if you pardon the poetic metaphor, which is to say that individual quanta hitting the reheating surface and perturbing it are modifying this sort of multitude of particles and radiation that subsequently ensue, and thereby wrinkle the cosmic soup and wrinkle the universe today as a result. You are one of those wrinkles, okay, at some very tiny scale. But it's hard to sort of track everything at the tiniest scales. We're going to track it at larger scales. We can look back at this cosmic soup, at least at the moment when the cosmic soup becomes transparent to light. Because at that point, light can leave the cosmic soup and travel to us at 45 degrees. And we can basically see a sphere of cosmic microwave background photons. And we can try and look at how it's been wrinkled by the wrinkled reheating surface. And similarly, we can look at the wrinkles in our universe on the largest scale of where the galaxies are grains of sand, and try and see what the wrinkles look like in that sense, okay? So here is the cosmic microwave background famously. As you look at it, you can see that it kind of looks like a random fractal. In fact, the contrasts, basically what you're looking at the cosmic soup, right? And as it's come to us, it's exaggerated by a factor of 10 to the fifth, so that you can actually see that the wrinkles show up. Otherwise, it would look completely uniform. So this is magnifying the non-uniformities, and one can study the statistics, statistically. One can study the quantum statistics that are imprinted there. Statistically, this is what the Planck satellite and its predecessor experiments have done. They're looking at the temperature of the cosmic soup here and there, and studying the statistics. But basically, it's a very nice fit to the theory of inflation, which says that the cosmic soup is just inheriting this picture of the reheating surface being asynchronized by quantum effects on the particles that make up the cosmic clock, or clocks, if you want. The simplest kind of picture of pair creation with no other interactions until you get to the reheating surface is basically captured by statistical correlations, which are 2-point in form, because there's 2 points in the picture, or so-called Gaussian correlations, where you're doing temperature correlators on 2 parts of the sky and looking at the temperature correlations. That's sort of what is studied here. There's a little bit of processing that's going on between reheating and the time of the CMB. But those are things that can be worked out using the model of the standard model in general relativity. The fit is very good. It looks like we really have come from this kind of scale invariant reheating surface, which inflation would predict. And in fact, the best fits would suggest that this Hubble scale of inflation can be as big as 5 × 10⁻13 GeV, which is about 10 orders of magnitude more energy than the LHC. So if we can use particle production during inflation as a laboratory, we have 10 orders of magnitude more energy for doing it than the LHC would allow us to do particle physics, okay? You might say it's only a constraint. Sorry, it's a constraint. Let's go back. I'm giving away too many things there. Okay. The simplest models of inflation actually saturate this bound. Okay, so it's quite possible, it's quite plausible that we are actually got this energy source in our universe. And similarly, if you look at galaxy structure, again, instead of temperature, you could use density correlations. So here is sort of a survey of the entire universe in galaxy clusters. And again, it looks like it has evolved from a kind of scale invariant reheating surface, okay? So it's not purely theory, there's a strong circumstantial evidence in the data to suggest that something like inflation happened. Okay, but I don't just want to see a pair of particles created and then nothing else happening. That's not an interesting life. This is an interesting life. This is in fact my life, okay? Because what I'm trying to say is this reheating surface, of course it's really three-dimensional, but it's a three-dimensional thing in a four-dimensional universe, and secretly it is keeping track of the timing of events. So if you know how to read this three-dimensional surface where large wavelength things happened earlier and small wavelength things happened later, then it is basically a kind of a hologram for time, okay? That is, there's a single snapshot which doesn't have time in it, the reheating surface, and yet if you know how to read it, it tells you about all of the preceding events and how they happen. So the cartoon is sort of, this is me as a baby. And since that happened earlier in time, the image of that on the reheating surface, if I lived during inflation, would have been bigger. This is me as a little boy, but it's smaller than this because it happened later. And so in some sense is on a smaller, is imaged in a smaller scale on the reheating surface. And this is me now. Okay, if I had lived during inflation, then my image would show up in a smaller way. Well, it seems pretty clear. Just use the smaller things to tell you about what happened later. The trouble is, the baby could have been born at any time. Okay, so there's baby me being born maybe slightly later, and therefore the image is smaller, or even later than that, or over here. And so the actual reheating surface is a crowded scale invariant fractal. If there's a baby on this scale, then there's a baby on any other scale you care to mention, okay? And it's all cluttered. So it's incredible that there would be the surface on which all the events prior to that in history are sort of being recorded in some way. But there's the problem of how do you decode the fractal clutter, okay? And of course, the answer is, oh, shouldn't you do some sort of Fourier analysis to sort of pick out big wavelengths? And if you filter on big wavelengths and small wavelengths, you can filter on early times and late times. So that's definitely the case, okay? But first, let's look at something that is easier than my life history, but not that much different, which is just the birth and death of a heavy particle during inflation. So here is the mc squared. If you have a particle whose mass is of order Hubble in this sense, then there's enough E equals mc squared to create this heavy particle pair. And then if they decay into inflatons, so here's a pair of inflatons in the decay of this, and here's a pair of inflatons in the decay of this, then these inflatons go and wrinkle the reheating surface, because these are the particles of the alarm clock. They wrinkle the reheating surface, and in that way, some image of this particle creation of this heavy particle is recorded in galaxy structure on the largest scales in the CMB. It's got to be sitting in there. But now, because there's sort of 1, 2, 3, 4 points of interest, they will be in sort of these 4-point correlators in the, say, density correlators of the galaxy structure. There'd be 4-point correlators rather than just these sort of Gaussian correlators. Okay, so somehow we're supposed to look into that. And basically, you know, this wrinkling of the reheating surface is making the constant density that would otherwise have been there into something spatially dependent, which makes life interesting because the atoms in your body are spatially dependent in density. In fact, there's something just technically, it doesn't make much difference for this talk, but I have to say it, technically there's something slightly easier, which you can get away with a 3-point function, because in the decay of the inflaton, there's a kind of stimulated emission effect. By what? Stimulated emission usually means there's some background of photons or something. Here, there's some sort of background of inflatons. And there is a background of inflatons. It's whatever is comprising this alarm clock, okay? The thing that looks like nothing, but secretly it's there, can provide a kind of Bose enhancement that allows you to sort of lose one of the decay products into the sort of Bose condensate of the alarm clock. It's not a big deal. It just says that you only need to study 3-point correlators, and so that's all I'm going to do. Okay. So this brings up the subject of primordial, which just means old, non-Gaussianity, which means 3-point functions or higher, not 2-point functions. And as I said, Fourier analysis is obviously the key to decoding something on a self-similar kind of picture, where you need to sort of tease out what happened at earlier and later timescales, which are imprinted on bigger and smaller wavelengths. So you do a Fourier transform of the 3-point function. There it is, and there are the wave numbers, K1, K2, K3. And up to something I don't want to define, this defines sort of what is called a non-Gaussianity usually, some function of the wave numbers rather than the positions. And it's always multiplied by a Dirac delta function, which ensures the sum of the wave vectors equals 0. Why? These wave vectors in quantum mechanics, the wave vector multiplied by Planck's constant is just the energy of, say, a photon, or here an inflaton. Here it's like an inflaton. So this is just momentum conservation. It's not a deep thing. Well, it is a deep thing, but it's a familiar deep thing. Okay. And so we can picture these 3 momenta or wave vectors as a triangle, since they add up to 0. So secretly, non-Gaussianity is a function of triangles in wave vector space. It doesn't even care about the orientation of this triangle because of rotational invariance, and it doesn't depend on the size of the triangle very much because of scale invariance. Okay, so it really is a function of shapes of triangles. What a cool function. It's a function of shapes of triangles. And just because it's a function, if you want to know what's the going rate of this function, how big is the function? Well, it's a function. We usually look at the equilateral shape. And just to quote something quickly, so that's usually called little f, okay? Little f NL, nonlinear. Okay, so that's the statistical approach to this subject. And it gives rise to this amazing subject called cosmological collider physics, which works like this. That remember that the sort of de Sitter space-time has this feature that the universe is expanding exponentially. Okay, so length scales and time scales are sort of correlated by this. And so these sort of inverse length scales or wave vectors, K1 and K3, say 2 sides of this triangle, are basically describing the timing of the late and early decays. If you, let's go, can I go, let's see if I can go back. Presentation. Yeah, this is good enough. For example, suppose I want to see this particle propagating, then I'd like all of this to happen early so that there's a clean, long line where the particle is just propagating by itself and then it decays. So I'd like to sort of have a late decay and an early decay. And we can do that, we can study that by having a large momentum and a small momentum. By the way, there's also K2. K2 is determined by momentum conservation. So if K1 is large and K3 is small, then K2 is also large in the opposite direction. But basically, the large momentum over small momentum will give us a kind of a late decay over early decay, or if you want, using just the the properties of exponentials, e to the time splitting. Okay. So if you look at the non-Gaussianity as a function of momentum, what you find, what would you expect? Well, what you'd expect just from your regular old quantum mechanics thinking is this factor here. There's a particle propagating a long time. And so this is the usual solution to Schrodinger's equation, e to the I energy times time over Planck's constant. The energy in this case is something like mc squared for this heavy particle. And the time it's going delta t. So that's this. This is what you'd expect. On top of that, it turns out there's this other factor, which is a kind of a suppression. It's not too surprising because it's not a big deal if the mass of if mc squared is comparable to Hubble. But if mc squared is much bigger than Hubble, it says, no, you can't have it. Okay, it's an exponential suppression. That's not surprising because H is roughly speaking the energy that's available for particle production. In a sense, what it really is, it's more like a temperature. It's like the temperature of de Sitter space rather than an energy. And so this is a kind of Boltzmann suppression factor. Okay. But anyway, as long as the mc squared is comparable to H, it's not a problem. If you try to take too much out of the space-time, if you want too heavy a particle, you're out of luck. So this is sort of what you might expect very crudely. And if you just plug in this formula, if you solve for delta t by taking logs in this equation and plug it in here, then you get this. You get a kind of weird non-analytic dependence on the wave vectors where the exponent is telling you about the mass of the heavy particle. So when you have complex exponents, as you know, that means there's some sort of oscillation as you vary the argument, okay? So this is a kind of weird behavior where you're studying the 3-point function, and if you can measure it, then you would see a kind of oscillatory or non-analytic behavior in the wave vectors, which is great. It means that this is what it means to be seeing the particle propagate. When you see this in this reheating surface, or in the fossils of the reheating surface called the galaxies or the CMB, what you're really seeing is this particle walking along, propagating along with Schrodinger's equation. Okay. But if the mass is very small, if this mass mc squared is very small, if it's very small compared to Hubble, then this whole thing is just 1, and you don't see anything interesting. Mc squared being much smaller than Hubble, you could just forget this exponent. On the other hand, if mc squared is much bigger than Hubble, this exponential is going to kill you. So that means there's a rough ballpark mc squared of order Hubble, which is your window of opportunity. Okay, that's the window of opportunity I was talking about. But this window is incredible because it could be as big as 10 orders of magnitude above the LHC energy. So the question is, can you see the non-Gaussianity? And non-Gaussianity, primordial non-Gaussianity, is not something we've seen yet because it is presumably small. Okay, and but we can ask whether there's prospects experimentally for doing much better, and there is. Okay, basically, when you're trying to measure this non-Gaussianity, this function of these triangles in wave vector space, you need a lot of data because you're trying to extract quantum expectations, which means you want to do the experiment many times. You only have one sky, only one universe, but you are able to get equivalent triangles by rotating these triangles, this triangle, or even stretching it because of scale invariance. So you do have multiple tries, measurements of the same thing, but you don't have an infinite number of multiple tries. So there's a kind of a precision you get by just having a finite number of attempts to do the experiment that you're trying to do to measure the correlator you're trying to measure. And so here is sort of a picture of the different types of experiments where Z is the redshift, which roughly speaking is the radial distance from us that the experimental data hails from. So at high redshift, or very early in the universe, is the cosmic microwave background. It's essentially a kind of sphere, that is to say, in the depth direction, it's like a delta function. And this is the CMB, and we get a certain amount of, it basically gives us a two-dimensional map, and this two-dimensional map allows us, we have enough data in it to get Fs of order 10, okay? And the current bounds on this non-Gaussianity are therefore of order 10. You haven't seen anything yet. But if you go to large-scale galactic structure, that is coming from this sort of more thickened or three-dimensional map closer to us from data from the galaxies that have already been formed and closer to us. And this is something that'll happen relatively soon, we will get data that will push us down by an order of magnitude or more, okay? So that's why it's exciting. And in the far future, we can do 21 centimeter cosmology, which is even more three-dimensional, and we'll push this sort of non-Gaussianity down to sort of many orders of magnitude smaller than today's bounds. Okay, so the prospects for doing something great are enormous. Okay. Now, the problem I first want to address is, what about that window of opportunity where all the masses of particles that you can create with this cosmological collider of order Hubble? Well, you have to be lucky then that particles that might be of interest to you are of order Hubble, okay? But you can try and ask, are there mechanisms that open this window to something broader than that? And there are, and so our work builds on these earlier ideas, referring to a kind of mechanism called a chemical potential. But our version of the story you can sort of picture here. And basically, instead of having Hubble provide the energy E equals mc squared, you basically have the heavy particle coupled to the clock field, the inflatons. And if you're coupled to the clock field, it's like saying, I have a clock in my room. My room is pretty empty, doesn't look like much is there, but I do have a clock, and the clock is at least ticking. Can I use the ticks of the clock as my source of energy? And you can. And amazingly, this cosmological clock packs a lot of energy, and you can actually get energies of order 60 Hubble. So if you couple the heavy particles directly to the clock field, you can produce mc squareds, which are between Hubble and 60 Hubble, which is a much bigger window. And in this way, you're able to probe, for example, mc squared. So here's an illustration, mc squared of 40 Hubble or mc squared of 5 Hubble. Here is K1 over K3. And here is the non-Gaussianity. And you can see the answers are all sort of order 1 in non-Gaussianity. So they're the kind of things that could be picked up by even the galaxy surveys that are coming in the next couple of years. And the energy reach, like we're talking about producing energies of particles, or the mc squareds of particles that we can produce, these kind of energies could be as big as 10 to the 15 GeV. We're starting to close in on the ultimate Planck scale of 10 to the 18 GeV, okay? It's amazing, okay? Now this has some fine print in terms of when does this mechanism that allows you to go to super Hubble energies, when is it allowed? I won't explain that right now, I'm out of time, but it's broadly applicable, and then there are many occasions where you can't use it. Okay. I just want to say one other kind of theory, grand unification, this question of unification of forces. Let me give you a quick sketch of our work in this area. So everybody knows about electric charge, and you may know that there are subtler analogs of electric charge when you come to the weak and strong nuclear force. So in the weak nuclear force, the analog of charge is called weak isospin, which sometimes is called up and down. And the analog of charge when you come to the strong nuclear force, or QCD, are the quark colors. You can call them affectionately red, green, and blue. And so these are all different types of charges, but these new types of charges have a kind of group theory subtlety that is not present with electric charge. Okay, so all of that is described, this group theoretic structure is described by what we call gauge theory. It's sort of the grammar of particle physics. And if you look at the charge assignments that the standard model particles, the particles that we've discovered, if you look at the charge assignments under these three different types of charges, they have some weird pattern, but all of that pattern is explained if you assume that these three forces are somehow remnants. They're remnants of a unified force field, okay, a unified force, where all these charges are interchangeable. Now, if you look at the different types of charges in nature, if you go to an experimentalist and you talk about these three different types of charges, they'd say, there's no way they are interchangeable. They look so different. They manifest in such different behavior, radioactivity, nuclei, atoms, they're completely different. And indeed, one quick way of tracking it is you can look at the strength of these forces, or the inverse strength of these forces, as we measure them in ordinary situations, but we can extrapolate it to super high energies. Okay. And when you do, you find experimentally, you put the experimental couplings that we see today, I mean, in ordinary physics, and extrapolate to super high energies, they seem to converge on each other, as if somehow at super high energies, they came from the same force. They had a unified origin. And so a simple theory that helps you explain this picture and this fact, okay? One of the simplest versions of this is, is a higher dimensional form of unification, or so-called orbifold unification, in which there's one more dimension. It's not the fourth dimension. Fourth dimension is time. It's the fifth dimension. It's one more dimension of space. But unlike the other dimensions, it's just an interval. It's a microscopically small interval of size L. And in this interval, the entire universe is sandwiched. Okay, so there's three-dimensional space in these vertical planes and this horizontal interval. Okay, and in this kind of sandwich universe, or five-dimensional space-time, there is a five-dimensional unified gauge theory, which is to say all the force fields are interchangeable. They're not distinct into electromagnetism and weak force and strong force. And of course, there's five-dimensional gravity. Okay, so this is the picture. Now, if you want to see this unified, if you want to see what it's like to have unified physics where none of the force fields is special, then you have to go to small enough wavelengths to get inside the fifth dimension. You have to have wavelengths smaller than L. But as you may know from quantum mechanics, if you think about a photon with wavelength lambda has a quantum energy given by Planck's constant over lambda, right? So to even have one photon that can penetrate inside here, you would have to have energies of order hc over L at least, per quantum of whatever you're going to look inside there. On the other hand, for energies much smaller than this this energy to go look in here, all of the different forces might look different if the boundary conditions, right? There's an interval, so there's a boundary at each end. If the boundary conditions break the interchangeability of force fields, okay? So if the boundary conditions distinguish basically give you 3 descendant forces, then that's pretty much all you see at low energies. But if you go to high energies, you're more dominated by what's going on in the bulk of the extra dimensions, where you can see this unification. And in a sense, that's what this picture here is telling you, that something like this seems to be going on. That at low energies, it looks like the forces seem to be very distinct because the boundary conditions are all that you see. But at high energies, it looks like there's a kind of uniform behavior of all the forces, of all the force fields. As long as we imagine that whatever is happening at this scale is basically the energy scale to look inside an extra dimension. And if we're lucky, that scale, you can see it's something like 10 to the 13, 10 to the 14 GeV, would be the kind of energy scale we could probe with cosmic inflation, with cosmological collider physics. So let me see if I can wrap it up then. So we have to identify this scale at which all the forces start to resemble each other as this 10 to the 13 GeV scale that experiments seem to be pointing to. Of course, on very long wavelengths, this picture, which is microscopic in size, looks more like this. There's just 3 dimensions. Here's a picture of you, right? You're completely unaware that you have any kind of thickness in the 5th dimension. So you go around saying, what 5th dimension? And for that matter, what unification? Okay. Unification is not apparent on long wavelengths, only on short wavelengths. Okay. So you can now ask, what is the smoking gun that this theory is true? Experimentally, what is the smoking gun? Well, the smoking gun is that you should try and look for some of these waves that are probing the 5th dimension. So we're going to use gravitational waves. And because these waves are secretly in a box, their wavelengths are discretized, as you're used to for waves in a box. There's a kind of an integer number of wavelengths to make up the size of the box. Then on top of that, waves are always waves are always made out of quantized particles. Electromagnetic waves are made out of photons, gravitational waves are made out of gravitons, and the energy of these gravitons with wavelength lambda is then given by hc over lambda, just like for photons, and you get a kind of discrete spectrum of energies for the gravitons, and this is what it means to see this mechanism, the smoking gun. If you're a large creature like us who doesn't know about this extra dimension, this energy looks like some sort of MC squared of this weird graviton that's propagating in the sideways direction. So that's what we worked out. That kind of graviton is called a Kaluza-Klein graviton. So we worked out the non-Gaussianity. And so you can work it out. Everything is in cartoons in my talk, but they're actual calculations, believe me. And the non-Gaussianity has some interesting form, which I plotted here, just going with the equilateral shape, showing you that as the mass changes, the non-Gaussianity drops, but at its best, you can get non-Gaussianities of order 0.1. If you remember, that's a little bit, that's something that can be pursued with 21 centimeter cosmology, but it's not yet something that could be done with galactic surveys, okay? The things that are coming soon. It also has a kind of angular dependence where angle is this theta here. And this angular dependence actually is symptomatic of the spin-2 nature of the graviton. So it's a very kind of exciting way of doing particle physics at enormous energies, probing grand unification. Okay, so I've run out of time. I'm going to just say this fast, which is another thing that we studied is, can we have stronger signals, please? We'd like stronger signals because there's only so much precision we can get in actual experiments that are coming soon. And indeed, the sort of prefactor that I didn't talk about is very sensitive to the inflationary dynamics. So one of the things we showed is that this sort of non-minimal inflationary dynamics called the curvaton paradigm or scenario allows you to get, for many different types of gauge theory signals, non-Gaussianity of order 1. That's the kind of thing that can be probed in galaxy surveys in the next few years. And we applied it to gauge theory. Now, I think I have run out of time, so I will not explain the subtleties of gauge theory that come from charge conservation and the need to break charge conservation, either with extra-dimensional boundary conditions or with a Higgs mechanism. And I think the last thing that I should point out is sometimes you're interested in the masses of particles that are much smaller than Hubble. So, like, for example, the Standard Model, wouldn't it be great to see the Standard Model in the sky? Well, the Standard Model masses are much smaller than this inflationary Hubble. They're only 200 GeV, not 10 orders of magnitude more. However, what we discovered is that there's a kind of mechanism which we called heavy lifting, where the masses of particles which are subject to the Higgs mechanism, like the particles we know and love already, they can naturally have masses of order the Hubble scale during inflation, even though today their masses are much smaller. The space-time expansion effectively lifts their masses up to the window of opportunity. And yet it preserves all the mass ratios. So you can sort of recognize the thumbprint if you could see it, Okay, so those are all sort of the different investigations we've gone through, and I'll just end here with these conclusions, just to say, this is a very ambitious program for both doing cosmology and particle physics. And my own work has targeted sort of what I'll call the prime targets: gauge theories, unified field theories, extra-dimensional theories, and trying to generalize all the mechanisms to sort of see what are our best prospects. It's important to say we don't know the mechanism of the alarm clock called inflation in detail. We have models of it, but we don't know which one is right. And which one is right greatly determines the strength of the signals and hence their observability. There's much more to do, I think, in the phenomenology. There's the understanding of all the sort of backgrounds, which in this game are called foregrounds. They're kind of the development of templates for these signals. There are generalizations of the field theory plot, etc. So all of this is still going on. I'm doing some of it, and I'm also trying to understand the field theory mechanisms in their greatest generality. Thank you.
Okay, so thanks, Raman, for the great talk. Any questions? Haibo?
Can I ask one?
Yeah, sure.
Raman, thank you so much. So one question I have is that, so in the last few slides, you commented that the production of the standard model particles, and because of the, they will get effective mass can be as high as like a Hubble constant. So would you like also tell us that with these productions, and do you see the non-Gaussianity just from the production of standard model particles, and how big the F will be?
Yes. So so these particles, the standard model particles with this heavy lifting mechanism would show up as a non-Gaussianity. The strength of the signal depends on which version of inflation is true. That's why I pointed to that as a sensitive one. But for example, we studied it, for example, in this curvaton scenario that I talked about, as well as a kind of agnostic scenario, best case scenario. And in both cases, yes, you would see it. It's an observable size of non-Gaussianity, either in sort of 21 centimeter cosmology or in some channels for some of the particles. You would even be sensitive to it in galaxy surveys. Okay. So the big unknown is which version of inflationary dynamics is realized by nature. Most of my talk, I will say, has been taking a kind of best case scenario, and sometimes even some of my research is showing how the best case is, what's the mechanism for the best case. But which of the inflationary dynamics nature chooses, we don't know yet. And so either we are going to have a very hard time or a merely difficult but still doable time. That's the quick answer.
Thanks. Yeah.
Other questions?
I should say there's a kind of irony in this slide that's up here right now, which is this heavy lifting thing. It makes you think, wow, standard model mass scale is a very flimsy thing. If you just go back early enough in the universe, suddenly the mass scale shoots up by 10 orders of magnitude. It's so fragile and unstable. That is exactly what is famously known in the standard model as the hierarchy problem. And usually it's called the hierarchy problem because we're trying to stop it from happening. But in this part of the story, it's actually an asset because it puts you into the window of opportunity. So, and it's a kind of way of probing the hierarchy problem. If you could see the standard model at very high energies replicated, it would mean that the hierarchy problem is not being solved.
True.
Other questions? Vivek?
Hi. I just had a quick question. Maybe you mentioned it or maybe I missed it, but the production of masses and particles that you mentioned, this mechanism, it seems inherently symmetric under matter-antimatter symmetric, right? So is there any mechanism for generating asymmetry in this?
There is. It's just you need a version of, for example, even in this picture, let me go back to this picture right. Oh no, this one right here. You see, here I've produced a pair of top quark and anti-top quark, and then they've sort of done something else. They've re-annihilated and given a Higgs boson and so on, right? So when you include interactions, the picture of production can get more complicated, okay? And indeed, we know of models in which pair production followed by other things can give rise to a net amount of matter versus antimatter. It is a beautiful subject. I actually learned I learned a sort of professional amount of it by working with Janu, who had worked on it before. But it's a very beautiful subject to find microscopic models which actually can work through the same process, but instead of just producing a pair of free particles, some sort of interacting story which can asymmetrize things. And it seems, I mean, I share your puzzlement, which is, it seems that at first, surely anything that works backward in time and forward in time, it's gonna be the same, it's symmetric. And it's beautiful to see that there is a kind of loophole where you can actually asymmetrize to end up with more matter than antimatter. But it is possible, but you need interactions.
Yeah.
Other questions? Okay, then I have a couple questions. So first is a follow-up with Haibo was asking. So Raman, did you mean that if there's a hierarchy problem that can solve the electroweak hierarchy problem, then the mass of standard model particles may not be raised up to the Hubble scale?
Correct.
In this mechanism, so the same mechanism will cancel out that contribution.
That is exactly right. This mechanism of heavy lifting I just talked about is taking advantage of the hierarchy problem not being solved. So if you solve it, for example, suppose the Higgs is a composite or something like that, right? These are that's a famous solution to the hierarchy problem. But if that happens, then it'll be much harder to lift these particles to faithfully. In other words, when I say faithfully, I mean with these mass ratios preserved. It'll be hard to raise all of the standard model into the window of opportunity. Now, you may see some parents of the standard model some ancestors of the standard model in the window of opportunity, but you won't see a faithful copy of the standard model in the window of opportunity. That's right.
So this apply for both bosons and fermions, or just for fermion you may have extra symmetry production that doesn't help?
For both fermions and bosons, yes. Or rather, for anything in which there is a Higgs, so it happens to be true. The standard model is a very beautiful theory, also a true one, in which every particle mass is sort of given by one fundamental scale, the Higgs expectation value. And if that gets lifted to some very high energies during inflation, then it drags everybody up in lockstep. There can be theories which are different from that, which are not all in lockstep, then different things can happen. But the standard model is rather special. Every particle mass is given by some fixed ratios multiplied by an overall mass scale. And that overall mass scale is very fragile, and in the early universe can get dragged up to a very high scale. I should just say that the game, if let's suppose everything goes your way, so that you get big signals and you can measure with considerable precision, which means you can measure the mass ratios and spins of the heaviest, let's say the top quark, the Higgs, the W boson, the Z boson. Let's suppose you see them in precision cosmology. And you can measure their mass ratios and even their spins. That would give you a heck of a lot of evidence to suggest that you're seeing the standard model. And actually those mass ratios, I said they're preserved. They're not quite preserved. There are some logarithmic running due to renormalization group effects. So you would even be able to, if you have enough precision, you would be able to see some aspect of that. And that would just be an amazing thing to see. I should say, for that to happen experimentally, all the winds have to be blowing your way. All the winds of fate. But it's possible.
So can I think about this M comparable to Hubble as some kind of thermal correction? You mentioned you can see the Hubble as this de Sitter temperature. Is there some kind of analogy? Because in thermal correction...
No. Yeah, in many cases it is like that, but in this case it is not. It is kind of a, instead of saying it's a thermal correction, it'd be better to say it's a curvature correction.
Oh.
And it's sort of just this, that in here's the Higgs field. Here it has some potential, and its usual potential is there's some sort of minus some tachyonic mass squared. Okay, so this is the so famous wine bottle potential of the Higgs, and all that's happening is you could have something that looks like this, where this is the space-time curvature, the Ricci scalar, and so this curvature correction, when this curvature today is negligible, you can forget about it. But during inflation, this effectively gives you a kind of different mass. And this curvature during inflation is nothing but h squared. So it basically takes the wine bottle, the famous wine bottle potential of the standard model, and it kicks it. But I don't think I can view this as a thermal. It's not even a subtle. It's not even the thermality is coming from quantum mechanics. This effect doesn't even have quantum mechanics in it.
Right. Just earlier on, you mentioned the de Sitter temperature is like Hubble. So I was wondering
it is.
The temperature.
But in order to turn that into a temperature, secretly there was an H bar. So it's not. I mean, it's true to say that H, the Hubble's parameter, has an aspect in terms of what it does, which is like a temperature. And it's a temperature, and whose temperature is it? Hawking's temperature of de Sitter spacetime, which is of course a famous quantum effect. But this one, you see, I'm just writing it in the classical Lagrangian. It's just a general relativistic correction to the standard model, which could be negligible today when curvatures are small and hugely important yesterday when inflation reigned.
Let's see. Okay, I do have more questions, but I think others can feel free to leave, and more people has more questions, you can stay around. But before that, maybe let's thank Raman again for the very nice talk. Yeah, so if you don't have further questions, you can leave, or if you can stay around, you can, if Raman is available, can talk a little bit more.
Thanks.
Yeah. So, another question I have is, you mentioned there's some mechanism you can push the mass scale, you can probe to up to 60 of the Hubble.
Yes.
Does that suppress your the F, because there's a Boltzmann factor, right? Or that formula need to be changed somehow?
Yes, in fact, that's why it was sort of, in fact, calling it a bolt. So it's useful. It's useful. It's useful to think of that suppression as a Boltzmann factor, or thinking of Hubble as a kind of a temperature is a useful guide, because the way to think about this is as a kind of chemical potential. Okay. I've drawn it like this because I just didn't have time to explain that in any great detail, but it's a chemical potential. I mean, for you, I can even tell you. So of course, you know that particle numbers in a thermal bath can be Boltzmann suppressed, but if you turn on a chemical potential, then you bias things and you can actually have a larger particle number. That's sort of what's going on. And the chemical potential is that you have whatever this blue particle is, you actually need a pair. That's why I said it doesn't always apply, but suppose you have a pair of blue particles so that they form a complex field. Then you can make a current out of them, right? If you have a complex field, then you can write down a current. That is what I'm calling J mu, and you can couple it to the inflaton like this. Okay. Now in the background of the inflaton, you will get J0 and dt phi, background. Okay, because again, this is literally the clock ticking. This is the ticking of the clock, but this is approximately constant. So it looks like you're writing in the Hamiltonian, you're writing something proportional to charge density, which is the chemical potential. So that's what I'm really pointing to down here. I'm pointing to this chemical potential effect. And it turns out that this energy scale, you might say, how big is this dt phi? How big is it? And the answer is, it is of order 60 Hubble squared. Okay, I mean, it's got units of mass squared, so of energy squared. So it's 60 Hubble squared. So that's where the 60 is coming from. You're secretly using the kinetic energy of inflation. You're sucking some of the energy out of the clock. Now, I think this may be the right way to say it here, but if you look at our paper, you'll see that the way of analyzing this, so compared to these early papers, which are a little bit hard to read, if you look at our paper, the way of analyzing this is we do a field redefinition to get rid of this effect. And it's a very nice field redefinition because it makes everything clear. It makes everything clear how you're getting this energy in a very simple way. I can go into it more, but just to say, the basic philosophy is you want chemical potential, and there's nothing stopping you from having this kind of coupling of the blue current to the inflaton. And then there's a way of analyzing it which makes life technically much simpler. And so our version of it is simpler, and the effect is stronger.
Okay.
Tell me if you want to know more.
Mhm.
But it's the philosophy is chemical potential is the one thing that can modify Boltzmann suppression.
One maybe a bit naive question. So then what you calculate 3-point function is the 3-point function of the inflaton, right?
It is the 3-point function of the inflaton, but as an intermediate, the intermediate line, if you want, is the heavy particle.
Okay.
So, yeah, maybe the quick way to say it is, normally if I were doing an S matrix scattering, I might have an intermediate resonance and in 2-to-2 scattering. So you would say, oh no, that means that there are 4 things, 4 momenta. Of course, if I said I'm doing fixed target scattering, so that I have a big luminosity effectively, right? Then they're down to 3 momenta. This is very much what's happening here. We effectively have a kind of high luminosity when you go to the fixed target. The fixed target being the alarm clock, the background inflation. Haibo, what was your?
Yeah, so I just so when you showed that the prediction from the Orbifold unification model predicted delta F is like 0.1, I was a bit surprised because this is in the limit like 21 centimeter, right? But the model itself also has very limited parameters. It's like just orbifolding scale compactification. Probably it's a gas scale. I mean, that's it, right? So
yeah, that's it.
Yeah. So it's is that just a coincidence that it just giving you like?
Well, look. So it is a coincidence that the unification scale in the non-supersymmetric case, the unification scale is roughly the window of opportunity for high scale inflation.
Yeah. Okay.
That is a coincidence, which is, and in fact, that story, which I compressed into those cartoons, it has a number of interesting features, even field theoretically. Just if you, because the Hawking temperature actually back reacts on the geometry. So I kept drawing the geometry as if it was just a flat slab,
right.
But it actually warps the geometry in a way. And that turned out to be a tricky problem. You have to be careful of how you stabilize it, et cetera, et cetera. So there's a kind of a backstory to it, but an interesting one. But basically it's what you say, that, yeah, we have experimental evidence pointing where the unification scale should be. And so it's just smack bang in the middle of where you would guess inflation would be. So you have a chance, to see spin two gravitons.
Yeah. But that is because yeah, okay. I just want to ask you, how that would depend on the model. I think, of course, if you're considering like orbifolding kind of model, apparently the heavy particle you have is, the KK graviton. Yeah. But can I like generalize in some way, for example, if you just consider like a 4-dimensional traditional unification, you also have like a triplet, doublet kind of splitting, the heavy Higgs to break the symmetry. There are also heavy particles at that scale, which
there's it's a funny thing, but in the traditional models, it is a very difficult thing. Remember, talking about 10 to the 13 GeV or 10 to the 4, even 10 to the 14 GeV, normally proton decay would kill you.
Yeah.
Sure.
So in the traditional models, proton decay kills you.
Right.
Whereas this sort of split multiplet approach in orbifold unification allows you to have baryon number. So in terms of what is the most plausible, simple-minded model of unification in that regime, the orbifold unification is vastly simpler than anything you can do just 4-dimensionally. So it makes it more plausible. But we also studied sort of the Z prime of SO10, B minus L. We also studied that as well. But the spin 2 thing is, shall we say, more exciting as a possibility because it points to the fact that if I see a Z prime, spin 1, I would say, okay, that's interesting, but it doesn't tell me exactly what was going on up there. But seeing spin 2,
yeah, it's more dramatic. Right?
It's more dramatic. It strongly suggests there's an extra dimension.
Yeah, no, that's right.
So again, I kind of, I my whole talk was full of exciting possibilities, and the qualification is that a little bit of luck has to go your way, but not crazy, just a little bit.
One curiosity is there any way you can the signal could be interesting when you have a mass much below the Hubble scale? Well, I mean, you talk about the standard model. Eventually, the mass can be a Hubble scale, but yeah, I just wonder.
But so other than this heavy lifting mechanism, so for example, it could be that the standard model does not get heavy lifted, right? But it's possible that there's some dark sector. This kind of physics is also like what you know from stochastic gravitational waves. It can see in the dark, right? So if it turns out that there's a dark sector, let's say it lives at 1,000 TeV, that's its Higgs scale. But it gets heavy lifted into the cosmological collider physics regime. But today, it may be sitting at 1,000 TeV. It may be hard to get at in any other way. But other than heavy lifting, I'm not aware of any way to see very lighter scales than Hubble. Either the Hubble scale has to be dropped by writing some very low scale inflation theory, or you have to raise the masses using heavy lifting. But I don't know any other way to do it. I should say, inspired by all the past work and so on, what we've been doing is we keep trying to generalize. So I don't even say that tomorrow somebody can't figure out another mechanism, because I don't know the whole story. I don't know all possibilities. Even this thing on the slide right here, this heavy lifting, this chemical potential story, to me, it was amazing. One day you didn't know it, and the next day there's a new mechanism. So it's kind of, field theoretically, it's very exciting. Experimentally, it's very challenging, but not hopeless. I mean, perhaps doable.
But didn't hear clearly. How does the Orbifold unification models prevent proton decay?
Basically, they use split multiplets, where, for example, suppose you have 2 5s, then the doublet zero mode in one. So the doublet and triplet, or quarks and leptons, come from different 16s. So let's say there's a 16 of SO10. That's your unification. But what happens is the quarks come from one of the 16. It come from a 16, and the leptons of that 16 are actually a Kaluza-Klein mass. The boundary conditions make the leptons of one of the 16s heavy, and the quarks are zero modes. And in another 16, the leptons are zero modes, but the boundary conditions make the quarks heavy. This is just by assigning the orbifold boundary condition, the even and odd parities of orbifold guts in different ways. So you can actually just have, in other words, it's completely consistent with having an unbroken baryon number.
My last question is, so just want to make sure, do you need to do this chemical potential thing to be able to probe the gas scale, or just the vanilla case would be okay?
Yeah. In the vanilla case, that's what I quoted you. The vanilla case was for this, like this thing that we worked out. That was the vanilla case. In fact, this graviton, if you like, because it's real in this example, you can't form the current that allows you to write a chemical potential. It's another way of saying that from a real field, if you try to form a current with a derivative and two fields, because it's the same field twice, it sort of disappears by, it's a total derivative. You need a pair of real fields or a complex field in order to form a current. So it doesn't apply in this, as far as the graviton is concerned, it doesn't apply. As far as some of the other things are concerned, it could apply. So for example, in standard SUSY guts, suppose you cared about SUSY guts, right? Then of course, famously, there's a complex field there, which is the Higgs triplet. And the Higgs triplet, you know, if you look at SUSY guts, then typically you would like the Higgs triplet to be a little, to do perfect unification, you'd like to have the Higgs triplet be a little bit lighter than 10 to the 16 GeV by an order of magnitude or so. So it's exactly something that could be reached in this way, because it can have a chemical potential.
Okay, that's interesting. Yeah, I don't think I have more questions at this point. Anyone else in the audience, you have questions to ask?
We probably should just let it.
Yeah.
Yeah. I do have, maybe I can look at the Raman's paper first, because the hidden sector stuff is really interesting. There's some freedom there, probably less constrained compared to standard model. And also you need to produce dark matter hidden sector particles anyway, so it's likely that thing will couple to the inflaton.
Yeah.
So this is kind of the model building and kind of was like exploring. I think it's very interesting.
Did anyone work on the dark sector stuff?
So we only worked on it in the sense that we were like, we got into the game